So my screen is visible, right? Hello. Okay, my screen is visible. So, okay, we are going to cover binary search in two classes. So basically, see, we have many things to cover in binary search. So the second class, this like in this class, we'll have introduction, and we're going to cover hard topics, which are only having binary search. So let me write this thing. So today we are going to cover, first of all, we are going to cover binary search. Like we are going to cover the algorithm. In this, we are going to cover algorithm. We are going to do some questions, and today we are going to do medium and hard questions for this. Okay. Then see, binary search comes with, there are other things also like ternary search, and there are interactive problems. So today I'm going to give you idea of both of these. We are going to solve a problem also on interactive problem. So what are these? Like we'll come into this in a moment, but there are interactive problems. Okay, there's ternary search. Then there is some advanced binary search. I'm going to give you an idea of this also today. We are not going to solve this problems on this. This will cover on next class, but I'm going to give you an idea on this. So you might feel like we are covering too much in today's class, but it's necessary because there are many things that have to be covered in binary search, and we have only two classes. In this, we are also going to cover what are some of the mistakes. Like many times our binary search, like the loop runs indefinitely. Like it doesn't terminate after some point. So we are going to look at some mistakes, you like very general mistakes that all of us makes. So these are all the things that are going to be covered today. Like I'm going to give you an idea of this. We are only going to have an idea. We are going to have an idea plus a simple problem. And today I'll try to cover more problems. Why? Because I feel like see, binary search, everybody is aware of what binary search is, but we'll do some hard problems so like nobody feels like they have they didn't learn anything in today's class. And as far as interactive problems are covered, I'm going to tell you what interactive problems are, and we're going to cover everything. But the advanced, like all of these three things will be covered in much more depth in the coming class. Is it okay?
Yes, yes.
And I'll like i I would like to ask you that try to keep this session as interactive as possible. Like if you have anything to say, like not like when I'm discussing something, when I'm in between a slide, don't unmute yourself at that point. But when I'm discussing the solution at that point, you can unmute yourself and you can interact with me. So let's start with this. Okay. So this is the basic introduction of binary search. So binary search is an algorithmic technique used to locate a specific value within a collection, within a sorted collection. And usually this collection is an array or a vector. And unlike linear search, which has a time complexity of big O of n in worst case, but binary search is having the time complexity of big O of log n. So this is much better than that big O of n. So now this is very helpful for large test cases. Like if we have something in order of 10 to the power 6 or maybe 10 to the power 18, you can apply binary search on it, and you can guarantee that like the solution will work if n is going up till 10 to the power 18. So first of all, let's see what linear search is. Like how is binary search different than linear search? So what is linear search? See, if you're given n elements like 1, 10, 11, 3, 5, 7, 2, and you have to find whether 3 is present in this or not. So what will we do? We'll go in this direction. We'll match this 3 with every index, like with every element. And if we find that this 3, like if this element matches with this 3, then we'll say yes, this element is present, right? This is clear to everyone. This is linear search. Is it okay? Okay. So now coming to binary search. So first of all, binary search only works on those arrays which are sorted, which are sorted in either in non-decreasing order or in in non-decreasing order or non-increasing order. Like it should be sorted in any of these two manners. So now once I sort this, if I write this as 1, 2, 3, 7, 10, and 11. So I can directly, like how does binary search works? Binary search simply works as I look at the mid. If the middle element is equals to this element, that is 3, it's fine. I can simply return. Otherwise, if this element, this middle element turns out to be more than this 3, I'll shift to my left. Like now only these are the elements that I'm worried about, right? All of these elements don't make any more sense to me because they will be always more than this current element. And if either way, like if 3 turned out to be like the element here turned out to be less than this element, then I'll shift to my right range. So this is how binary search works. I'm not going to go any further in this because this is more than enough. Like binary search, what is binary search? But now let's come to how how to apply this binary search on our answer. How to apply this binary search to find our answer. So let me go back to the slides. First of all, how does binary search works? So we begin with a sorted array. We compare the middle element of the array with the target value. If the middle element is equal to the target, then we have found it. If the target is less than the middle element, we eliminate the right half and we go back to the step 2 on the only considering the left half. Otherwise, if we find that the target element is greater than the middle element, then we eliminate the left half of the array and we repeat the second step considering only the right half. So we keep on continuing this process until we found the target or our array becomes empty. If our array becomes empty, then the element is not present in the array, otherwise it is. So this is how binary search works. Coming to like how can we connect this to like how to apply this on binary searching on a basically on binary searching an answer. First of all, see, we can connect this if you're binary searching, we are in like either having our array in increase order. These are the values, okay? The values are increasing here. They are non-decreasing. So these are the values. So we can apply binary search on this. So if you want to apply binary search on our answer, the final, like let's say if f of x is the result, and if you want to apply binary search on our answer, that is this result. So by default, as we saw earlier, that the array should be in sorted order. This function should be monotonous. Now, what is monotonous? What is monotonous? A monotonous function is, there are two types of monotonous function: monotonous increasing and monotonous decreasing. So monotonous increasing function is that, let's say this is f of x and this is x. So if there are two values, x1 and x2, and if you find the value at f of x1 and you find the value at f of x2, if suppose this value is more than this thing, so you can, if x1 is less than x2 and f of x1 turns out to be this thing, then you can assume that this complete function will be non-decreasing, like the values will be non-decreasing over this range, over the complete range. So this is monotonously increasing function. Similarly, monotonously decreasing function is the complete reverse of this. So it is something like this. This f of x are the values at these points. Is this thing clear? What is monotonously increasing and monotonously decreasing functions? Okay. So now, why should we like the function be monotonous? So see, if the function is not monotonous, like what we did initially, we looked at a point that is a mid, and from that we were able to tell that we can skip this range, right? So similarly, in this also, if our function is monotonous, then by looking at some point, we can tell that this complete range is not not any use to us, right? So then we can completely ignore this and recursively call our function for this range. And we keep applying this till we have a single point in our range or we have no point in our range. If we have no point, then the answer is like we haven't found any answer. And if we have a single point in our range, then we say that is the answer that we were looking for. So now let's look at this using an example. So coming to this, now we have to find the maximum x such that f of x is true. Basically, this is what we are doing, right? So let's say we have a Boolean function f of x, and usually in such problems, we want to find the maximum or minimum value of x such that f of x is true. So this function, don't worry about what this function is. This is just some function, and f of x, like it's just like for a value of x, it will give you either true or false. Now we want to find what is the maximum or minimum value of x such that f of x is true. So now similarly to how binary search works on an array, that is a sorted array, binary search on answer only works on if the answer function, that is f of x, is monotonic. That is either it is monotonically increasing or monotonically decreasing. So these are the steps. We want to construct a function last true such that last true of low high f will give you either true or false, and this returns the last x in the range low to high such that f of x is true. And if no such x exists, then the last true function should return you -1 or low of -1. That is something that is not in this range. And this can be done with binary search if fx satisfies both the conditions. So if f of x is true, then f of y should be true for all y less than or equals to x. And if f of x is false, then y should be. So basically, if you have a function like this, and this is some x, so if f of x is true, then for then like basically monotonicity means that for all the values that appeared before this, the value should be true. If at x f of x is false, then all the values after this should be false. So this is basically monotonicity. And yes, it can be vice versa also. Like for this part, it is having false. If you're having a false here, if you're having true here, then all the future values should also be true. But it shouldn't be like if you're having a true here, then you have some jumbled values here or in this range. Then binary search is not applicable. So without wasting any time on this, I'll just quickly go through one of the basic implementation of binary search. So this is the basic implementation of how this function works. So this is the last true function. This is low, high. You're currently in range from low to high. This is a function Boolean. You don't have to worry about what this function is. This is just a Boolean function, which is monotonous. Now, if none of the values in the range work, we have to return low -1. So this is basically for that. Now, while low is less than high, we pick a mid value and we check for this mid. So if this function returns us true, then we can change our low to mid, because we want the maximum at which, like maximum value for which this function will give us true. Otherwise, if this function gives us false, then we will change our high to mid -1. So I think we have already we are already into the session for like around 10 minutes. Is it 10? And yes, it's around 20 minutes, and this is everything the basics of binary search. So you can ask me questions right now if you have any questions regarding the things that I've covered till now. Otherwise, we are now going to move to how to get the time complexity actually. Okay, why low -1? See, low -1 is basically at this, like, it doesn't actually matter if at this point you can have an answer variable also. This is one of the implementations. In this problem, like initially we have to return low -1 if nothing is found, right? So at start, if we do low -1, then here you'll return low -1 if this function never returned true, right? Otherwise, you will return some mid. No, if you're not using low -, then you'll do low is less than equals to high. Yes. So let's go to the complexity analysis. So now how to actually prove that your binary search algorithm works in O of log n. See, binary search divides the problem size by half in each step, right? So leading to a logarithmic growth rate. So let me show this by help of a diagram. So basically, initially you had a range of length of size n. You had assumed that you had n elements, right? So in each iteration, you are picking a mid element. Then you are either removing the left part or the right part, right? So okay, I'll cover this the different calculations. Like I'll cover everything in a moment. Like you'll see many questions. We are going to discuss, I think, around 5 to 6 questions today. So don't worry about it. So at each iteration, we are going to either remove this left range or right range, right? So if initially we had n elements, then after one iteration, we'll have n by 2 elements, then n by 4, then n by 8. So each time the elements are getting halved. So how many times do you think these iterations will go? This will be log base 2 n, right? So if you look at the time complexity, if you write this as O of big log 2n, this is same as if you write this as O of log n divided by log 2, right? So basically, if you have O of k times, where k is a constant, into some log of n, you can write this as O of log n. So this k here is 1 divided by log 2. This is a constant. So that's why we say the time complexity for our binary search function or binary search algorithm is O of log n. So now going forward, okay, now let's cover some problems first. Then we'll go these things. So the first problem that we're going to discuss is, okay, let me open that problem. So this is that problem. My screen is visible, right? The problem statement is visible to you. Okay, so let's look at this problem. So in this problem, we are given that we have an array A of n integers where n is odd, and you can make the following operations with it. So we have to choose one of the elements of the array, for example, AI, and increase it by 1. So these are the operations that we can do. We can pick any element, increase it by 1, and we want to make the median of the array as large as possible after using at most k operations. So the median of the odd sized array is always the middle element. Like after you sort it, it is the middle element. So we want to maximize that thing. Now we are given that there are these many elements and k will go up till 10 to the power 9. So how to solve this problem? Any idea? Like right now is the time to discuss. If you have anything to say, you can say it right now. If you have n elements, randomly
Can
we
you
are given.
repeat the question?
What?
Can you repeat the question?
We have n elements and you are given a value k. N is going up till 10 to the 2 into 10 to the power 5, and k is going up till 10 to the power 9. So these k are the number of operations that you can do. You can pick any element and increase it by 1 in one operation. Finally, what you have to do, see, after doing all of these operations, you have to find the median. So you have to maximize this median. And what is the median? Median is nothing but if you're given n elements, you have to sort the elements and you have to pick the center element. Is it okay?
Yeah, okay.
And n is always odd in this problem, so you'll get only one center element. How do you think that we'll solve this problem? Any idea? Like, you can unmute yourself, and if you have to say anything, instead of writing in the chat, just unmute yourself.
Hello.
So first of all,
Yes.
hello.
Yes, yes,
Uh,
yes.
I guess we will apply binary search on the median. Then we will check if we can convert that median in the number of operations we are given.
Okay, yeah, I get it. See, what we can
Hello.
do in this. Yes, yes, yes.
So first of all, we'll sort the given array,
Okay,
and then we'll start with the middle element, and we'll try to make it equals. Suppose we'll try to make it equals to mid. So in order to make it mid, we should the elements which come after it should be greater than equals to mid. So we should try to equalize all the make it greater than the middle element.
okay, let me explain. So, see, let's see what our function is going to be. See, first of all, we are given n elements. Then, out of these n elements, what we have to do? We have to do some k operation on these, and in each operation, we'll increase it by like each element by some. We'll pick some element, we'll increase it by 1, and finally, we have to maximize our median. So let's say maximize our median. So let's say I'm applying my binary search on answer, right? So my answer is median here, maximum median, right? So first of all, you have to identify this thing that your answer is median, maximum median possible. Then after identifying this thing, what will we do? So let's say low is initially something, high is initially something, and you'll try to find that is, like I said, your function f of x should return true or false, right? So for f of this mid will give you this is whether or not this median is possible or not. Whether or not this mid is possible as median or not. This is your function will give you. Mid is possible as median. So, okay, we know we have our function and we know how binary search will work, right? If now it's same, right? For mid, we'll check for mid. If f of mid is true, then our low will be mid plus 1. Maybe our answer can be mid. Otherwise, else our high will be mid minus 1. So this thing is clear to everyone, right? There is this function which is going to return us this thing, and this is how our binary search will work. So first of all, is this thing clear to everyone? Okay. Now, when I was discussing binary search in the initial slides, we didn't worry about this function. But usually, writing this logic is easy. Now you have to think about this logic. What will go inside this function? For binary searching on an array, what is the logic of this function? The logic of this function is basically if you're given n elements, you're matching that whether this element is equals to this element or not. So basically in this function, you simply do whether ai is equals a of mid. We'll write this as a of mid. Whether a of mid is equals to x or not. So this is this function in that case. But now what we have to see that whether or not this mid can act as this value can act as a median or not. So in order to do this, see, we have some values. Let's sort these values. After we sort these values, let's say there are total 7 values here, right? So first of all, these 3 values are of no use to us. Why? Can anyone tell me?
Because we want maximum.
We want to maximize the median. So we want to maximize this element. So we'll always increase these elements, right? These are the bigger elements. Why increase these 3 elements? So
if that does not affect.
What? Like, why will you waste your operation on these elements? See, finally, if you are having 5 as your median, maybe 5, 6, 6, 7. Why? If you are having 1s here, if you are having maybe 3s here, so you are having 5 only as your median, right? You're having 5 only as your median. So why waste your operations on these elements, making them 3? Do you get my point? Okay. So now the thing is, we have n elements. Let's just sort them. And from these points, we'll try to make every element more than or equals to this mid value. This is the median, right? So we'll know how much operations are required. The number of operations required on these elements are nothing but maximum of 0, comma. Why 0? Because it's possible that all of these elements are already more than mid. So mid minus the value at this ith position. So we'll add all of these operations, and if finally operations turns out to be less than or equals to k, we'll say that it's possible to have this as our median, otherwise it's not. Is it clear? Is it clear? So I'll show you the implementation. I'll show you the complete logic, but I won't waste time on that because the logic is like the implementation is not that useful. The code. So now initially my low is 0 and high is 1e10. So this is also one of the most important things, that you should choose your low and high such that this is the maximum thing that can be your answer, and this is the minimum thing that can be your answer. If you don't pick your low and high correctly, your binary search won't give you correct answer for all the test cases, and that's why sometimes you'll get wrong answer on pre-test 2, or maybe wrong answer when system testing is going on. And I'll always suggest you try to pick, like, don't be conservative here. It does, like, if you're not like sure whether to take high as 1e9 or 1e10, always pick the bigger value. Why? I'll tell you. See, if your low is 0 and high is 1e9, so the number of operations are log base 2 1e9, right? This is nearly equals to 32. Even if you bring this number to high is equals to 1e18, now your number of operations will be log 2 1e18. This is nearly equals to 64. It is less than 64. So this is actually just twice of it. So if your algorithm originally was running in n log n, now it is running in 2n log n, right? So never be conservative when you're giving low and high, because might be it's possible that the high value that you took, the answer is actually more than this. Like, it's also possible that the final binary search answer will be more than this, or maybe it's less than this thing. But usually you don't have to always do this thing, right? Because if all my array values are up till 100 and the size of like the n is also 100, then you don't have to take 1e18. 1e18 is just like overkill for this thing. You can take around 1e5, 1e6. But if the values, if you're not sure, then during the contest, always go with more values. But usually this thing is the maximum thing that can be your result, and the lowest thing that can be, like the lowest part of your range and the highest part of range. Is it clear? Okay, so let's go back to our implementation. I'll be covering implementation just for these purposes only, like so that I can teach you something, not for the code. So we'll just quickly go through this. We are taking A as input. Then, as I said, that we have to sort. Our function should be monotonous. So you'll have to sort it. Then check of mid will give you whether or not this is possible as one of the medians or not. So how to do this? These are the needed operations, and we are adding median minus this thing from mid to n, right? And if finally this number of operations needed is less than k, then you can return true, otherwise return false. So this is the function that I showed you initially in my introduction slides. This is binary search, and this is the monotonous function. So I think this should be clear, right? So let's go and look at some other problems. Now, first, I'll cover some things. Okay,
Yes,
needed.
sir.
Yes.
Sir, can you tell me when to use low equal to high and when to use low less than high? I am confused about it.
Okay, I'll come to that. Is one of the things that I'm going to cover in mistakes. I'll come to that in the later part of the session. Okay.
How do you choose the value of mid?
Mid is always low plus high by 2. Like you can
Because
see.
in some submissions they use L plus R plus 1 by 2 too.
Yes, you're talking about this thing.
Yes.
High by 2. In some, we take this thing, right? You're saying
Yes.
this. So it depends on the implementation. It depends. You are taking, what are you doing here? If you are having low is less than high, or low is less than equals to high, it depends on that. But I'll give you my thing, like what I do always, and it always works. Okay, don't worry about these things. Like I'll cover this thing in mistakes, and I'll give you my like how I solve these problems, and it will always work. You don't have to think. So let's talk about, first of all, I'm going to talk about ternary search a little bit. We are going to cover ternary search much more in detail in future, like in the second class. But let me give you an idea. See, binary searches basically, when our function is monotonous, right? When our function is monotonous. Now, ternary searches when our function is not monotonous. It's basically a parabola. If we have a parabola, then ternary search is applicable. So let me show you what a parabola is. A parabola is, for some part, like the function first decreases and then increases, or for some part the function first increases and then decreases, and you have to either find the maximum this point or usually this point. So this is ternary search. So how we do ternary search? See, initially same, we have some low and high. Okay, let me write this here. So we have some low and high. Like I said, these are the end points or the corner points of your range. Then instead of taking one mid, you take two mid 1 and mid 2. So mid 1 is basically, you can take this as low plus low. Okay, let me write this. So we can take this as low plus high minus low by 3, and this is high minus low, high minus low by 3. So basically, if I show you these mid 1 and mid 2 here, if this is our low, this is our high, this is our mid 1, and this is our mid 2. So we check answer at these two positions. And now I'm not going to connect like I connected my binary search function with that first initial binary search, right? And then I showed you function, and then I showed you in which range we have to shift. I'm not going to tell you right now in which range we will shift, but basically, since we are dividing our answer, like each time we are dividing our this range by 3, you can guess out that the complexity for this is usually log base 3, something like this, n, right? For ternary search. But what is the, like, two things should be clear to you right now. When is, like, for which functions is ternary search applicable? We cannot apply binary search on this. Why? We cannot apply binary search on this. Why? Because this is not monotonous. Hence, ternary search is applicable if this function is a U-shaped function. So first of all, this thing should be clear. Second thing is, instead of having one mid value, we have two mids. We have two mid values, and these are those two middle values. Mid 1 and mid 2, yes, of course. See, you can take this as some x. X is basically 1/3 of your range. 1/3 of your range. If L is this thing and R is this thing, this is your range. This x is 1/3. So you're adding 1/3 to your low, and you're subtracting 1/3 from your high. So mid 1 and mid 2 are always these. Like they always lie in between your range.
Hello, sir. Hello.
Yes, yes, yes.
So in the mid 2 formula, there is high minus. Is there in bracket for that? High minus 2.
What can you?
In the mid 2 formula, we have written
Yes.
that high minus.
Yes,
high
yes,
minus
yes. This thing, like this is only getting divided.
That's bracket is there.
Yes,
there
yes.
in bracket?
Yes,
Okay.
actually, I have a chat opened. Like I'm looking at the chat, so that's why I'm not able to. Okay, let me shift it here. So this is there. Okay. And yes, ternary search will only work on parabola functions, like the functions that are parabola. It won't work on third degree. Like if you have something like this, like you'll have to modify your algorithm, but directly ternary search won't work on this thing. Binary search, like binary search doesn't even work on that parabola functions. Is it clear? See, all these things, that is it possible that minimum value will lie after mid 2? Yes, it's completely possible, but that's a part of implementation, and that I'll have to show you by first connecting the logic with a function. See, it's completely possible that we have something like this. Low is here, high is here, maybe mid 1 is here, mid 2 is here. So in these cases also, your ternary search works, but I'm not going to cover it right now. That is for the next class. But you have an idea of ternary search, right? Like today we have to cover advanced topics of binary search only, so that's why I'm skipping this. And we have to cover iterative problems also a little. But the thing that I wanted, like, is the basics of ternary search clear to you? I just want you to know that ternary search in problems that are involving ternary search, you cannot apply binary search. Okay. So now coming now, okay, since we are discussing right now, I'll say that we'll discuss interactive problems also, and then we'll move to the problems, like solving problems again. So coming to interactive problems. So first of all, what are interactive problems? See, interactive problems are something. See, what is the usual way in which you are given problem, in which you have to solve a problem? You're given an input, and using this input, you have to output something, right? In interactive problems, we are not given the input directly. What we are given only a part of input, and then we have to ask the compiler about some queries. Like we'll ask compiler that give me the value between this range or the result for this range, and then the compiler will provide the answer only for that part. And using that thing, we'll have to somehow get the final requirement, get the final result. But we have to ask the compiler for some values that give me the, like, let's say if you have to find, if you have to, like, you can ask the compiler what is the sum of this range, what is the sum of this range. So like, let's say you have to find whether or not there is any negative element in your array. So how to do this? If this is an interactive problem, this is, see, anybody, there are no constraints. You just have to find out whether there is a negative element present or not, and you can only ask for a range more than 2, more than or equals to 2. Okay, how will you do this? Any idea? Okay, I'll repose the problem statement. So the problem is, you're given n elements, you don't know what are those n elements. This is basically like, you don't actually, you're not given the input. So you just know that there are 100 elements, okay, and you don't know what is the order of those elements or what those elements are actually. You just know that there are 100 elements. What you can ask the compiler is, you can give a compiler a range I to j, and the range should be more than or equals to 2, and the compiler will give you the sum of elements in this range. And finally, you have to find what is the position, or if there exists a position which has a negative element in this array, in the original array. See, if the range was equals to 1, if you could have asked just for one element, then you would have just asked for each and every point, right? And if at any point the compiler gave you the sum of this one element as negative, then you would have said, okay, this is one of the positions which is having a negative value. But in this, we can only ask for range more than 2. So how do you think we can do this? Doing this is simply takes, like, start taking positive sums. Like, first start from this part, what is the sum of this, then ask what is sum of this, what is sum of this. If at any point the sum decreases from what it was initially, you'll know that this element is negative. Is it clear? Like, for all the prefix, you should ask what is this sum. But there is a corner, like there is one case which is missing. You are not actually finding whether, what about these two elements. So in order to find for these two elements, you can do separately. First find the sum of these two things, then find the sum of these three, and then finally find the sum of these four. This way, these two elements will also get covered. So for each and every element, you'll know whether it's positive or negative. Is it clear? So this is basically a interactive problem. And now let me tell you, 80% of the problems that are usually interactive are binary search problems. And interactive problems are usually, like, the rating of these problems start from 1700 and they go up till 3000. So you'll find hard problems only for interactive problems. But the thing is, like, there are also some easier problems which are in 1500 range. But if you know binary search basics, you'll be able to solve interactive problems up till 1900. Why? Because interactive problem itself is a different topic and many people don't actually know these things. So instead, like rather than, like, these problems getting more submissions because they are interactive, they don't get that many submission. But the logic behind these problems is very easy. So let me cover one of the interactive problems first. Like, we'll solve one interactive problems.
Sorry, could you please repeat that? What is the interactive problem?
You, like, just repeat yourself. I couldn't hear you.
Could you please repeat what is the interactive problem?
Interactive problem is nothing. You're not like, okay, let's cover this problem and you'll know. See, we are not given the complete input at once. We are just given a part of input, and then we can ask questions to the compiler. Like, we can ask questions that give me a value for this range. Is it okay? Like, you'll see in this is an interactive problem. So let's read this problem. I'll share the link to this problem in the chat also. So before the last stage of the exam, the director conducted an interview and he have gone n piles of stones. I think this should be got. He gave, no, it's okay. He gave gone n piles of stones. Now the ith pile is having AI stones. So each stone is identical to and weighs 1 grams. So each of these stones is exactly same and it's just weighed 1 unit. Now, except for one special stone that is part of an unknown pile. So first pile has 1, second pile has 2 stones, third pile has 3 stones, fourth pile has 4 stones, fifth pile has 5 stones. So all the stones in a pile are identical and they weigh 1 gram. But there is a one stone which is hidden in one of the piles and it is weighing 2 grams. Now, Gon can ask director questions of the kind. He can choose K piles and the director will tell him the total weight of the piles chosen. And finally, Gon has to find the pile that contains the special stone. So, however, the director is busy and he can answer at most 30 queries. And n is up till 2 into 10 to the power 4, and the number of stones in each pile is given to you as this. So, first of all, n is 2 into 10 to the power 5, right? So, once you read this and you are only required to make, like, you can only make 30 queries. So, you'll know that this is a binary search problem, right? Because log of 2 into 10 to the power 5 is less than 30 only, right? But how to solve this? See, what you can ask for each pile, you know that this has 5 stones, this has 6, 7, 1, 3. You can ask that what is the sum of second, third, and fifth pile, right? So if the second, third, and fifth pile sums turns out to be 14, then the stone that is different from every other stone is not present in any of the 3 piles. But if this turns out to be 15, then that stone is hidden in one of the 3 piles, right? Yes, no, anything?
Could you repeat this one?
See, if you are given n piles and you know each of the piles is having this like first pile is having 5 stones, second pile is having 6 stones, third pile is having 7 stones, and if you ask the director that okay, give me the sum of total weight of these 3 piles, if the director give you the value as 14, then you will know that the stone which is different is not present in any of the 3 piles. Why? Because the sum is 14, right? There are 14 stones, each stone weighing 1 gram, so the total weight is 14. But if the weight turns out to be 15, then you'll know that there is at least one stone. Since there are 14 stones, but the sum that the total weight is 15. So you will know that there is the stone which is different is hidden in one of the 3 piles, right? Now tell me, how will you solve this problem? Okay, someone is saying prefix sum. How will you use prefix sum for this? If you use prefix sum, you'll have to ask for each and every, like for first you'll ask for this, then you'll ask for this, then you'll ask for this. So you'll have to ask n queries, and n is up till 2 into 10 to the power 5. You cannot ask more than 30 queries. You can ask only 30 times.
We can divide the array in 2 parts. First ask for the left sum and then right sum.
Yes, exactly. Okay, you don't actually have to ask for both parts. See, once you divide your array into 2 parts, you ask the sum for this part. If the sum turns out to be, okay, we are not asking for sum, we are asking for weight. If the weight turns out to be the number of stones in this part, the total number of stones, then you don't have the different stone hidden in this part. So in that case, you will directly shift to this. You don't have to ask here. You can directly shift to this range. Otherwise, if the weight is not equals to the number of stones, you will consider this range. How to get the total number of stones? You can use prefix sum. Is it okay? Is it okay? Yes, no. And also let me know at this point, this is my are you feeling my am I going too fast or am I going too slow? Or is it okay? Okay, so let's get back to this problem. So we know we can get the weight from the director. We'll know the number of stones using prefix sum. If in this range, these two things turns out to be same, then we know that the stone that is different is hidden in this part. Otherwise, it is hidden in this part. Okay. So now how many queries we are asking? We are asking log 2 n, right? We are asking log 2 n. N is okay. How we are going to the half part of the array? I'll show you. I'll just show you in a moment. Okay. So yeah, we are increasing. Actually, we are just working with low and high. If initially low is this, high is this, and mid is this. If we find that the weight of the total weight of this part is equal to the number of stones, we'll change our low from this to this position. Now this is our low. So we are now working with this range. Is it okay? Okay. So the complexity of this is log, like the number of queries that we'll ask is log 2n. So this is actually, if log, you'll see log 2 into 10 to the power 5. it was 2 into 10 to the power 5, or it is, yes, 2 into 10 to the power 5. So can anyone tell me what is this thing? Just quickly, what is log base 2 into 10 to the power 5? I think it will be around 26. No, will be around 20. Can anyone check? Yeah, 17, right?
18 approx.
Yeah,
17.
17 point something. So it's actually 18. So in 18 queries, we'll know our answer. So I'll show you the implementation now. I'll cover the implementation of this in much more depth. Why? Because this is the first interactive problem that you're seeing, and this is important. So first, let's start from here. So first, we are taking our input. So we have taken n and a as input. Now, this is prefix sum. Prefix sum is useful for me when I'll want to know what is the sum of a range from L to R. So that's why I'm calculating this prefix sum vector. So prefix sum is simply like for each index, you will know what is the sum of elements from 0 index to this index, to the ith index. Get sum is a function that will return you the sum of the total number of stones from L to R. I'll come to this part in a moment. So my low is initially 0, high is n-1, because these low and high, as I told you, these are actually the corner, like the leftmost that thing can, like the thing that can be your answer, and the rightmost thing, the highest value that can be your answer. Since we have to answer that, we have to find the index which is having, we have to find the pile which is having a different stone. Our answer can be either the first pile or the maximum answer can be the last pile. So the low is 0 and high is n-1. Answer and mid, these are other two variables. So now my mid is low plus high by 2. I ask what is the sum of this, what is the total weight of this thing. I'll come to this ask function in a moment. Then if this turns out to be more than the sum of this thing, I say that the answer is mid and high is mid minus 1. That means I'm shifting to the left part, left range. Otherwise I'll shift I don't have my answer right now. My answer is like this can be my answer. I'm not 100% sure, but this is one of the possibilities. Here, if this value turns out to be more than this, like this value turns out to be equals to this value, then I'll change my low to mid plus 1. So now coming to this ask function, this ask is, you have to implement this ask function in all of your interactive problems. You don't actually have to implement another function. You can write it here also, but usually the logic gets more complicated and like it gets messier if you include this ask thing in your binary search function, binary search loop only. So what is this ask function doing? This is just like, this is given to me in the problem statement that we have, when I'm asking something, I have to print a question mark. So you print a question mark, then you print the length of your range, like what are the number of elements. Then you print the indices that are in your range. Then you have to always flush your output. You have to print endl. Why? Because usually what we do this thing. Interactive problems, this won't work. Why? This is basically like, what this means is if you do \n and if you use that fast input output in C++, the compiler doesn't, like when your like code is running and the compiler outputs a cout statement, it doesn't actually print anything. It stores that in a stack, that is output stack. It's actually a queue, I think. Yes, it's output queue. So it stores in that. Why? Because see what happens. Okay, I'm going a little off topic, but it's really important because otherwise you'll see that you're getting time limit exceeded in interactive problems. So once you write a cout statement and you use a \n, what happens is this thing, whatever you are printing here, what you are trying to output here goes in an output queue. And it actually stays there. Nothing is printed at that point. Your code gets like, it keeps running, but nothing is printed. It is stored in this queue. And once your program gets terminated, or once your program finds a statement which is having an endl, then your code, like whatever thing is pending in this output queue, prints. And why this is important? See, once you have written fast input output, what happens? See, fast input output, this is basically how fast input output increases the execution time of your code. What happens? See, you have some lines of code and you have, let's say you have some cout statements, some 10 to the power 5 cout statements. So each time when your code encounters this, it has to turn out to printer, it has to print it, then come back to here and start the terminate, like the execution from again, from again. So the time which is expended in going from this place to this place and again returning back to this place is very high. Otherwise your code runs very fast, right? So this is what fast input output does. What it does, it just keeps running your code and it doesn't print anything. It prints everything at once. So you don't, like the compiler doesn't have to switch from this place to this place again and again. So this is how fast input output increases the execution speed of your code. But if you use fast input output in your interactive problems, what will happen if you use this thing in your interactive problem? You'll ask something, that is, you'll output something as question mark, you'll print some range that I want to answer from this I to j, but this thing doesn't actually get printed. Why? Because you have used fast input output. So you'll actually have to print this thing. So in order to print this thing, either don't use fast input output, or you can use endl. If you use endl, then the output get flushed. You can also use cout.flush. This is a function, like everything which is in the queue will get printed at that instant. So you want this to get printed, because then only the compiler will know what is the thing that you're asking for, and then the compiler can answer that thing. So is it okay? Don't use fast input output in interactive problems. Is it okay? That's why I'm using an endl here after this. So once this is done, you can take input, like the compiler will give you an input and you can return that value. So basically ask is doing, you're asking the compiler for this range, you're printing the indices, and you're asking the total weight. Then like this I've already covered. So now once you have found your answer, you cannot print question mark, right? So you'll print an exclamation mark telling the compiler that you have found your answer, and now nothing more, then the program can end. So if your answer is correct, you'll get an accepted thing, otherwise you'll get a wrong answer. So if you ask more queries than 30, you'll also get runtime error. So this is how interactive problems work, and these are really easy problems if you know how to solve these. And around 80% of these problems are around binary search only. So I'll move to the next part. Interactive problem is clear to everyone, right? Yes, no, anything?
Sir,
Yes.
I have a doubt, sir. How did the compiler is giving us answer?
Yeah, it is giving on that thing only. When you're outputting, when you're printing something, it keeps looking for input, what you're printing. It keeps looking for that thing. And once you print something, like you print IJ, it first checks whether it is valid or not. If it is not valid, it will simply give you wrong answer. Otherwise, if it's valid, like your range is valid, your query is valid, then it will give you some X value. So you can read it.
It means that it means that it is storing in some data structure.
No, you don't have to worry about how this is like working in compiler, because it is not storing anything in data structure. It is basically another code. It is the code that the problem author has already written. Like it is also reading that what is the range, and it will give you the sum of that range.
Okay.
Yeah, it's also, it's like you can assume it as it is another code which is working parallel to your code.
Okay, sir.
Okay, ask and prefix sum calculation. Okay, so I'll quickly go over prefix sum calculation. Prefix sum is nothing but, first I'm taking sum of, like every prefix sum of I will give me what is the sum of elements from 0 to I, and this will give me what is the sum of elements from L to R. So how to get this? Just subtract prefix sum from prefix sum of R, just subtract prefix sum of L minus 1. So I think this is clear, right? Now going to ask. So ask function is nothing but, you have to first print a question mark. This means that you're asking something. Then in this problem, you first had to print the number of files that you want the total weight of. Then you have to print those files indices, and make sure that you're using an endl here, or you're not using that fast input output. Otherwise, your code doesn't actually print anything here. So you'll get a TLE eventually, because your code didn't actually print anything. So the compiler didn't provide you anything, so you won't be able to read anything here. Okay, what is not first input output? I'm talking about fast input output. Fast input output is that C in dot null. You use that, right? C out dot null, C out dot tie null. That is fast input output. Okay, I'll give this to you in chat. So let's go ahead. Now we'll be covering interactive problems much more in depth in next class. But you have till now you should have an idea of when binary search is applicable. That is only on monotonic functions.
Hello.
Then yes.
Why it is returning sum only? Why not others thing?
Where?
Even in the question for the args function
In which
the
part?
given range. In the args function you written now. Why it is returning sum only?
It is not like it is giving me the total weight. Like in the problem statement is given, we can ask the compiler what is the total weight of the piles. So it is giving me that thing only.
Okay. Fine.
It is the input basically. You can consider it as an input. Okay. So till now the things that should be clear to you. Binary search works on monotonic function. What is f of x, like the function? How to apply binary search. Then we covered ternary search, basic ternary search. So the basic should be clear. You should be clear that this works on U functions, the functions which have U shape. then it should be applicable. Like you should know that binary search doesn't work on this. Then interactive problems should be interactive. What are interactive problems? What are interactive problems? You should know. You should know how to apply binary search on these and how to print, how to actually write the code. So these things should be clear to you till at this point. How to write code. So if we have already we are now around half time, so we have completed around 1 hour and around 10 minutes. So are all these things clear to you? I'll share the complete code of interactive problem. Okay, don't worry. Okay, how to debug interactive problems? So interactive problem debugging is little more hard than the usual problems. And what I'll do, I'll try to show you how to debug interactive problems in the next session. Okay. So this is around 70% of what we had to cover today. Now the remaining 30% is common mistakes and plus problems. So around 70% of this was theory. We have covered theory and we have covered some examples. Now the problems that we'll solve are not just examples, but they are in order to increase our logical thinking, like how to think about, like when you see a problem statement in a contest, how will you know that you have to apply binary search on that, right? And I'll share all the problems links that I'm going to cover. Don't worry about those things. So, and you might feel that I'm going a little fast, but believe me, there are many things that can be covered in binary search, and I like to cover each and everything so that nothing is missed, because this is binary search is one of the most important topics. And believe me, you can watch, you can read the blogs of high-rated coders, you can read blogs of LGMs, and you'll find one thing. They have many times said that in order to be an upper-level expert, you just need binary search. You just should know how to apply binary search efficiently. You don't need any other data structure, anything else. If you know this thing, you can solve majority of the problems. Because this doesn't actually, binary search is not just an algorithm. It will increase your thinking capabilities. It will increase your problem solving skills. So let me get back to the part. Okay, let's first, should we first discuss the common mistakes, or should we go directly to the problems right now? What should we do? Okay, let's cover some common mistakes and then we'll go to advanced problems. Okay, there is one more thing right now left, which is advanced problems. I have to cover this thing also today. I'll give you an idea of this thing. I won't cover this thing in depth today, but I'll give you what is advanced problems. But first, let's cover mistakes. So now covering mistakes. See, we don't know when to apply while, when to use low less than high, and when to use while low less than equals to high, right? So basically, what I'll suggest you, follow this template. While, see, first of all, let me give you a difference between these two. This is basically when you want to check for your high also, when you want to check for your endpoint also, then you do this thing. But rather, I'll suggest that don't worry about whether you want to check. The best way is you declare your variables as low, high, mid. These are the three variables that everybody will declare, right? Declare another variable answer also. Now, what will you do? While low is less than equals to high, always have an equals to here. Then if your function is working for mid, calculate your mid here. If your function works for mid, the first thing that you should do, make your answer equals to mid, always. And then maybe change your lower boundary, and in else block, change your higher boundary. And finally, instead of printing low, print your answer. This thing will always work. You will never end up having a TLE, or never end up having some wrong answer or something. This will always work. Take another variable answer. Is it okay? And this is easier to debug also, because you can print your answer values. Why low less than equals to high sometimes gives you TLE? Because what we are doing mid is equals to low plus high by 2. So if low is equals to 1 and high is equals to 2, you can take some numbers. These are not actual. Then if, okay, this is low. If low is equals to 1, high is equals to 2, and you take mid, then mid will be actually equals to low plus high by 2. This will also be 1 only. So if you change, if you're doing low is equals to then mid, so actually you are not changing your low. So it will be your low won't change, your high won't change, and you'll keep running your loop. You get my point? Because this is basically taking, I'm only working with integers, right? So this will take the lower bound. This is this thing, right? Is it okay? Now, looking at why, like you would have seen this thing also. When should you use this thing? So this thing is actually a part of advanced binary search. When we are not working with integers, I'll cover this thing. Maybe I'll cover this thing a little bit today, but basically this is advanced BS. This is like, actually this is not one, this is some error. So actually using r minus l more than 1 is same as low. If you're working with integers, this is same as writing this as low is less than equals to r plus 1. L plus 1 is less than equals to r. So this thing doesn't actually make sense for integers, but this thing is very useful when you're working with error. So I'm not going to cover like error, what is error here right now. Let me first cover all the common mistakes. But this is a part of binary search. And that's why I'm trying to cover many things. Like I'm covering things fastly because we have to cover these topics also. Like you would have found those problems, right? Try to answer, like your answer will be considered correct if it's close to 0.00001, right? You would have seen these kinds of problems. So we have to cover those problems also. So first of all, going back to the common mistake. So first mistake was when to use low, high, right? Second thing. So just give me a minute. So now the second thing is when our answer is, so the first mistake you'll find it as, if you like read through the documentation, the first mistake is off by 1, whether to use equals to or not. Like you have to use non equals to. The second mistake is you are not accounting for negative bound. See, my range can start from negative values also. Like I said, your low should be the least possible value that can be your answer. So you shouldn't blindly assign your low as 0. Is it okay? This is one of the most common mistakes that people, like we have a template of like something like low is equals to 0, high is equals to 189, and we apply binary search. Don't apply binary search blindly. Then the third mistake is, this is clear, right? Let's look for the what should be the lowest, that can be the lowest possible value. Then is integer overflow. See, if your low and high going up to 10 to the power 18, make sure that your mid is also a long variable. If your mid is an integer, you'll have an integer overflow and you'll get random values. You won't get correct answer. See, if your low and high are up till 118, then in your while loop, make sure your mid is also a long variable. Is it okay? Okay. One more thing. So this is not a common mistake, but this is, instead of writing your binary search functions each time, you can use inbuilt also. Like if you have to find what is the element which is more than or equals to in an array A, you have to find the first position which is having element more than or equals to, let's say, E. Don't use your, like, don't write your own binary search for this. Use lower bound. I think you like knowing what is lower bound here, right? You know what lower bound functions are. So if this is what you need, use lower bound. Otherwise, use up. If you just want more than, use upper bound. So this is not a common mistake, but this will be useful when you are trying to save time. You don't actually have to write everything from scratch. So these are the common mistakes. So after this, let's cover. First, I'll try to cover those advanced things that I just told you, and then we'll move to some problems. So first of all, see, many times you're given a condition that you have a function fx, you know this thing, and you want to get, this is the answer, and you don't actually have to answer. Like you're not working with integers, but you're working with floating point values. So these are decimal values. So in these, you cannot actually, like, see, if you directly work with mid, like if you work with something like low is something, high is something, and you are working while low is less than or equals to high. If these are integer values, then this is okay. But if these are not integer, these are double values, then this condition won't actually be ever true. Like it will be true maybe after infinite time, right? Because if you have 0 and 1, low as 0 and high as 1, low as 0 and high as 1, and these are decimal values, your mid will be 0.5. You'll change your low to 0.5, then your low will be 0.5 and high will be 1, right? Now your mid will be 0.75. This will, like, if you look at this will be something like, if this is 1, your mid will start from 0.5 and it will maybe go like this. Okay. It will go like this. like after infinite operations, it will get close to 1, but it won't be actually equals to 1, right? So this thing will, this loop while low is less than equals to high will go on indefinitely. So in these cases, if we are given decimal values, we don't write our function like this. We write it like while high minus low is more than the error that we want. So error is usually something like 10 to the power minus 6. Is it okay? So while the difference between these is more than the error, we'll keep applying binary search. Otherwise, we'll stop. Is it okay? Now you might think, if high is 1e9, low is 0, what is the complexity of this thing? Applying binary search like this. So actually, if you're going up till this, see, each time your range gets divided by 2. So initially your range is of size 10 to the power 9, and you have to go till 10 to the power minus 6. So it's nothing but 10 to the power 15 log base 2. So the total number of operations will be this thing. So this is around 50, right? So that's why this kind of solution works very quickly. But there is another case also. Maybe, see, you can directly run a for loop also for iteration 1 to iteration less than 50 and iteration plus plus. So instead of having while low less than, like high minus low more than equals to error, you can do something like this also. This will also make sure that your error is finally less than 10 to the power minus 6. Is it okay? If you're, like I just showed you, right? If your range will get divided by 50 times. Is it okay? Yes, no?
That what?
Yeah, this is for decimals.
Hello, sir, could you repeat please?
Yes. Okay, like I showed you, if you want the error less than 10 to the power minus 6, then the total number of operations will be around 50. You can calculate the log of value of this, logarithmic value of 10 to the power 15. So that we can use a for loop, and we'll do iterations 50 times, and everything which is inside this while loop will move it inside this for loop. So we are making sure that we'll do, like, in each case we'll do 50 iterations of our binary search, and finally we'll get our error less than 10 to the power minus 6. This is pretty advanced. I'm going to cover this in next class also, but just this is also one of the syntaxes. Is it okay? Iteration plus plus. This is iteration. This is not I plus E. This is iteration, ITE. Is it okay?
Can you explain how we are getting 10 to the power 15 and log 10 to the power 15 operation?
Okay. See, initially your range was of this size, and finally your range should be of this thing. So what is the factor by which your range got decreased? It got decreased by 10 to the power 15 times, right?
Yes.
So each time you are decreasing your range by 2. So how many times you will have to do operations? You have to do operations these many times, right?
Yes.
So what are the total number of operations? 50 log 2 10 to the power 15. Is it okay?
Yeah.
Around 15. Is it okay?
Yeah.
So I'm saying, instead of using a while high minus low less more than equals to error, we can use 50 operations like this. So this is also one of the syntaxes for advanced. Like usually when binary search comes to our mind, we only are doing like this, right? While low is less than equals to high. So for advanced, we either use something like high minus low is more than or equals to error, or we do for and we iterate 50 times, 50 or 60 times. That is more than enough for our error to be less than 10 to the power 6. Is it okay? Is it okay? Yes, no?
So that means that for 50 times we will calculate the mid and check the answer.
Yes, and we'll try to decrease our range.
Okay, sir.
Okay,
We will not use the while.
No, we
while
won't
condition.
use while. So I'll show you the implementation also. So this is the advanced implementation. So if you look at here, like this is same as the implementation that I showed you here using while loop. So this was the basic implementation. The same thing is done here, but it is done using if I have some allowed error. So initially I have an error of this thing. Then while my error is more than this, I'll keep doing this thing. And my difference is, like, I'll keep decreasing my difference by 2. Instead of doing this thing, I can also directly make iteration, like I can make this loop go 50 times, right? Because I know after 50 times, my difference will be less than my allowed error anyway. So do you get it? I'll cover this thing in next class also, but just be aware that there is this kind of syntax also for advanced binary search. Is it okay? What about others? I'm only seeing few people in the chat. like you don't have to, I'm not saying that you should be like completely 100% confident with advanced implementation. I know this thing, like probably majority of like many of you won't have seen this thing earlier. It's okay, we'll cover everything in next class, but I'm giving you just an idea right now that this kind of thing also exists. This thing, like it is for this loop, like this function only, like this problem only, this won't be in all the cases. So don't worry about this thing. You can just look at this, how we are getting our error less than the allowed error. So now let's go back to solving problems. We'll cover problems now. Okay, the time is already, like we have around 1.5 hours we are already covered. So now let's see this problem. Okay, I think this is not that good problem. I'll give this problem to you as a daily problem. We'll go to some other problem. Okay, this problem. Yeah, this was actually a Microsoft OA problem. So we'll cover this problem. So I initially thought that I'll cover each and every problem. Like I thought that I'll cover this problem also, but like these two problems are similar only, and I'll give you this problem as a daily task problem only. Okay, because we are running out of time. So let's cover this problem. So in this problem, we are given that farmer John has built a new farm, built a new long farm with n stalls, and the stalls are located along a straight line at positions x1 to xn. Now x is going from 1 to 10, 0 to 10 to the power 9. Now his C cows don't like this barn layout and become aggressive towards each other once put into a stall. To prevent cows from hurting each other, FJ wants to assign the cows to the stalls such that the minimum distance between any two of them is as large as possible. So we have to find what is the largest minimum distance that we can get. So first of all, is the problem statement clear? Yes, no, anything? Okay, it's clear, right? So see, basically you have some x values. There are some, this is the 1 to 10 to the power 9 range, and in this you have some stalls, and you have to find what is the maximum distance between two cows that you can get if you like put cows in these stalls, if you arrange the cows in these stalls. So how to solve this problem? You have C cows and n stalls, and C is system equal to n. C is the number of cows.
So we will finally search over the answers, means
Yes,
the
okay.
distance between the two stalls.
Yes. Okay, it's okay. So we'll binary search on our answer. We'll do while low is less than high. While low is less than high, we'll find the mid. Now, how to write this function? How to write this function? This is the most important part of binary search. How to write this function? So basically, we know what is our mid here. Our mid is, can we get this much distance between two cows or not? How to do this?
If the position of the current cow minus the previous cow is greater than equal to mid, then we'll count the variable, and if it is equal to the total number of cows, then we can return true.
Yes. Yes. So initially, you have to put one cow here, and then try to move along the values, the sorted values of x. If at any point, you can find that this value minus the previous value, that is this value, turns out to be more than or equals to mid. You place your second cow here. Now your previous value is this, and similarly, you will keep on going forward. Finally, you can check if the number of selected values are more than or equals to C, then you can place your cows. Otherwise, you won't be able to place your cows. Is it okay? And if you use lower bound, it will be much harder. Like you'll have to use lower bound again and again. So this way, it's easier. So I'll show you the implementation directly. So okay, this is the implementation. So in this, I am first taking n as input, then I'm taking those x values of x as input. Then after sorting these values, initially my low is 1, that is the distance will be 1, and the maximum is higher x of n minus 1. So this is one of the, like, see, I could have taken this as 10 to the power 9 also, but I took it as x last value. That is the biggest value of x, this thing. Because anyway, you cannot have more than this distance. If your first cow is at this place and your last cow is at this place, the distance between two cows cannot be more than this value. Is that fine? Like you get this, right? So that's why I have taken high as this thing. Now, while low is less than high, I find the mid. Then I'm looking at this possible value. Like I'm checking if it's possible to have this as my distance between each and every cow. Then if it's true, I'll do my answer as mid. I like initialize my answer as mid, my low as mid plus 1. Otherwise, my high will be mid. Finally, I can print my answer. Now, looking at this possible function, see, right now I have done. Done means that how many cows I have arranged. And previous is x of 0. I'm going from 1 to n minus 1. If x of I minus priv is difference, is more than or equal to difference, I'll increase by done and I'll make this as my previous. If at any point I find that I've arranged all the C cows, I'll return true. Otherwise, I'll return false. Is that okay? If you like, if anyone is having any doubt, ask me right now. Otherwise, I'll move to the second problem. Okay. So let's go to the next problem. So, this is the next problem. So in this problem, we are given that we have n books, each with number ai, and ai number of pages, and m students need to be allocated continuous books with each student getting at least 1 book. Out of all the permutations, our goal is to find the permutation where the student with the most books allocated to him gets the minimum number of pages. Out of all the possible permutations, we have to find this kind of permutation, okay? And we have to return -1 if a valid assignment is not possible. And the allotment that we are giving should be contiguous order. So let's look at this example also. So assume that we have 4 n as equals to 4. So we have 4 books. Then we are given these are the number of pages, and this is the number of students. So one way to do is we can allot 12 to first student and 34, 67, and 90 to another student. So maximum pages is 191. Are you getting this?
Yes.
So now the another way is if we allot 12 and 34 book, like the book with pages 12 and 34 to the first student and 67 and 90 to the second student. So then maximum pages will be 157. And otherwise, this is one of the possibility. So we find that the answer, like the minimum of these is 113. So now our problem is out of all of these possible ways, we have to find the minimum number of pages among, like for all the students, like each student will get some pages, right? So we have to minimize the maximum pages that a student is getting. So you get the problem statement, right? Like, is anyone having any doubt in the problem statement? Okay, like let me know if you want me to discuss the problem statement. No, right? Right, right, yes. Okay. Right, yes. Okay. See, you're given some books. That is n books, and each book is given like this book is having a1 number of pages, this book is having a2 number of pages, up all the way up till a of n. Then you are also given that there are m students, and you want to give books in this order. Like one student will, like each will get a continuous block. So if there are, like if we have something like this, the first student will get these books, the second will get, if we had 5 students, the third student will get this book, the fourth student will get these books, the fifth student will get these books. So let's say this student got 6 pages, this got 10, this got 3, this got 7, this got 9. So this is the maximum number of pages that a student is getting. We have to minimize this thing. So is the problem statement clear now? So basically you have to divide your array of size n into sub-arrays such that the sum of the maximum sum that any sub-array is minimized. Is that okay? So how to solve this problem?
The answer is always gonna be less than.
Same as the previous one, we will.
Yes, we can solve this problem exactly the same way we solved the last problem. We'll binary search on answer. Our low will be like minimum, let's say 0, high can be 10 to the power 9. And for mid, how to, like, let's write this mid function. I'll write this with you guys. So function of this mid. So basically this is telling me this will return true if I can have this as my minimum number of pages. Like any student is not getting more than these pages, right? So I'll have x as the count. I'll have count, and then for int I is equals, or I'll simply do, okay, I'll have one count variable which is initially 0, which is how many students have been given the books, and I'll have another variable which is sum. How many for the current student? How many pages has he received? So then after this, what I'll do for int I is, or I'll do for int e of a. I'll write this auto for auto e of a. So see first, if e is more than the mid value, then I can simply return false, right? Right? Yes, no, anything?
Yes.
Okay. So then I'll simply return false. Otherwise, I'll check if sum, that is till now, sum plus mid turns out to be sum plus e, right? Sum plus e. If sum plus e is more than mid, then I'll make my sum as 0 and I'll increase my count. That one student has been, like, the number of books that would have been given to the previous student has been complete now. I cannot give any more books. Otherwise, here I'll do sum plus equals to e. Finally, I can check if count is less than or equals to the number of students. See, I'll return true, otherwise I'll return false.
Hello.
Yes, yes.
In the case if sum plus e is greater than mid, we can assign sum equal to e.
Yes, but I'm doing this here, right? So otherwise you'll have to write else here. But I'm directly doing this for every case. Either way,
Okay.
I'll add e here.
Okay.
So, like, you were able to come to the solution very quickly, right? Because now you know when to use binary search, what are the usual cases on binary search, and I'll show you what is the, like, this is a hard problem in GFG. So the rating of this problem is around 1900. If you like, if this problem appears in code forces, the rating will be around 1900. If you don't have any idea about binary search, you won't be able to solve this problem. So that's basically, if you like, that's what we had to cover today, when to use binary search. And this is the, like, advanced problems of binary search, like, not advanced, but these are the hard problems of binary search. So if you know some topics like when to do binary search, when to, like, what are interactive problems, you'll be able to cover problems up to easily up to 1800. Then there are some things like advanced binary search that we'll cover next week, which has those decimal things, and problems of those are around, I'll say, around 2000 rated. So we'll cover that in next session. But there is a little thing that, like, 2-3 things that are left, so we'll cover that for now. There are some problems that I wanted to discuss today, but since we don't have that much time, so we'll cover, like, I'll give those problems to you as daily task problems. Okay, is it okay? Okay, so let's look at some advantages and disadvantages of binary search. So advantages of binary search are: it is efficient for large data set, it is optimal for situations where data doesn't change frequently. See, if data changes, you'll have to again sort your complete algorithm. So if it is changing many times, you'll have to again keep on sorting your array, right? So in that case, binary search won't work, because instead of having just log n complexity, you're having n log n for sorting. It is ideal for situations with limited memory. See, in all the solutions, we didn't use any extra memory. So it's ideal for when the situation is when the situation is giving you limited memory. The disadvantage is you need to have sorted data set. There is no other way around this. You should have sorted data set. It is inefficient for unsorted data, and insertion and deletions are more complex and costly than in linear data structures. So algorithms which are working on linear search, or like which are having linear data structures, they tend to have easier insertion and deletions. But as I said, in binary search, it won't be that easy. Now coming to some applications. So the applications are, like, these are real life applications. So searching is like in databases, binary search is implemented. In libraries also, like that, lower bound and upper bound, those are implemented using binary search only. Then there is finding the element in games, like guessing games, like I showed you, that are interactive problems. So binary search is used in those. Then there are mathematical equations like finding square root. So I'll cover this thing in next part also, but it is really easy. Like, sometimes what happens, if you use inbuilt square root functions, you'll get wrong answer because of precision error. So how to overcome that? You can write your own square root function. I'll show you that thing in next session. And then there are network routing problems. So if you're from CS background, you'll cover this thing in your courses. So I think that's it for today, and we'll cover everything, like in advanced binary search and ternary search and interactive problems little more in next session. Is it okay? And did you felt like I was going slow or fast today? Like, I was going a little fast because we had to cover many things, and still I was not able to cover 2 problems that I wanted to discuss.
Hello.
Yes.
Yeah, I actually asked a question about the first problem we solved. Median something the name was. how to
Your
calculate
voice is too. Can you please like speak a little louder?
Yeah, sure. We solved the first question, median something. Can you go to the question?
Okay, just give me a second. I'm sharing that feedback form for today's class in the announcement section. So kindly fill that also. Okay, just give me a minute. Yes. So you are talking about the first problem that we discussed today, right?
Yes.
Okay. So this was this problem, median. Yes.
Yes, this one. Here we calculated the operations we needed. How did we calculate this one? It will be more clear for me if you run it with an example.
Okay. See, basically in this problem we had to find what is the maximum median that is possible, right? If we can do k operation. So once we sort our array elements, so the first two elements are of no use to us. So we'll try making each of these elements more than k. So if we have something like 1, 3, 5, 5, and 7, and we want our median to be 6, then how many operations should be done here? It should be 1, right? And how many operations should be done here? It should be 1. So total 2 operations are required. So we are just checking that this 2 is less than or equals to k. If it is, then we can make our median as 6, otherwise we cannot. Is it okay?
Yeah, but in code we just checked the middle one.
Yes. No, not the middle one. All of these elements. Like I'll show you the code also. This was the code. So we are going from mid to n. All the all the elements in the right part of the range. We are checking for all.
Okay, I got it. Thanks.
Okay, so that's it for today. So thanks for joining. And in case in case you still have doubt in binary search, you can raise a query and tag some mentor in it. But still, all the things that are covered as advanced binary search today, they'll be covered in much more in depth in next class. I think we'll have next class tomorrow only, so you don't have to wait much for that. So I'll announce the timings really soon, and it will be most probably it will be tomorrow only, and we'll cover the advanced things in that. So that's it for today. Thanks for joining. Bye bye. Okay, I'll share the interactive code right now itself. I'll share it in the code because after that, because I can forget it later. Just give me a minute. I'll share it. I'll share the complete code. You can copy it. Okay, I shared it in the chat. Okay, so bye. And we just saw a little bit of advanced binary search problems, and we have completed binary search at this